Okay. Hi, this is an introduction to the aligner drainage tool. These tools are a step of one-touch plugins that goes through the drainage process. From there are some tools that help with facilitating the layout of the system, and then tools that bury the system and size the pipe. In this presentation, the tools are exploded so that we can see it step by step. But it is possible for all of the steps to be in one program, one click. All right, so a couple of reminders to use this as where the tools can be found. The tools can be found on the Illinois Drainage Guide, and they can also be found in the QGIS repository. And there are instructions there on how the tools are to be installed. So the first thing is for doing the design, there has to be a boundary layer for the field, a raster DEM that for getting elevations, and then one has to create a lateral layer and a main layer, or both layers in one. Okay, this tools can be used for simple layout, so where you have like one main with a few laterals or several laterals, or complex systems where you have mains and submains and laterals. So for here, we'll go through the tools with a demonstration field. This field is a field on the South Farm located at the university, and data is available for actually going through the example with this field, and there's a link here for getting the data for doing this example. The tools themselves are a series of each one is a one-click plugin, and they follow after each other, and they're in this exploded mode, so one can see the steps involved in getting a drainage network. The part one of the tools, there are 4 tools that are used for facilitating the layout of drainage systems. There's a tool for coordinate harmonization, one for boundary extraction and LiDAR thinning, plotting and visualizing drain nets, and creating tile overlay grids. And these facilitate the layout of a system. So for coordinate assignation and harmonization, the objective is to make sure that all the layers are in the same coordinate reference system. Coordinate reference system that is usually used for this, or should be used, is a coordinate system in feet. The latitude, longitude are themselves not distances, but angles. And so they should not be used for drainage design. This is optimized for use in feet, although they can be used in a metric system if the DEM is metric. Most of the DEM which are available for design in the US are in feet, or are in the English system. So this system is optimized for the English system. And what this tool does, it takes all the input layers, and then it makes sure that they are set in the target coordinate reference system. The next tool is a boundary extraction and LiDAR thinning. In Illinois, for example, LiDAR maps are available for Illinois and for almost all of the contiguous United States. In Illinois, the LiDAR the LiDAR maps are at 4 feet cells. And for drainage design, these are massive files. And if used at this scale, it makes the process quite slow. And so what is usually done is to thin out the system. And it can be thinned out anywhere to 25-foot or 40-foot cells. This routine, it thins out the DEM, and it determines also the output can be gotten as a thin DEM or as CSV points, XYZ points that can be taken into another design program. For each of these tools, each of these tools usually have 3 sections. There is a section for the input, there's a section for specifying the output, and a section for explaining the steps that should be taken to run this plugin. Then after the input has been specified, then the run button is pressed and the output is obtained. And this is the same for all of these tools. The next tool is one for plotting and visualizing drain nets. The drain nets consist of the contour systems as well as the ley lines. And these ley lines are the flow paths on the soil surface. And by using these 2 tools together, then it is easy to visualize the topography of the land. This tool also identifies any depressions that might be in the field as well. This is an example of the difference in contour lines between the 4-foot DEM and the 40-foot DEM cells. As you can see there, in essence, the information is the same, but especially for presentation purposes, the 40-foot cells provide a better visual image than the 4-foot cells. In speaking to some contractors, they says that in general, they use 40-foot cells for presentation and 12 to 20-foot cells for actual calculations. It's also possible to label the contours, and the contours can be labeled using standard QGIS procedure, and which is just to, this is fairly standard in QGIS. The next tool creates overlay grids, and these grids are set at the required spacing. So there are usually 2 grids created, one which is vertical and horizontal, and one which can be set at any angle. This grid can be used to get to do regular space tiles in the digitization process. And it can change from section to section. So if one section of the field, the contours are at an angle, then one can use the grid at that angle, and then the grid angle can be changed during the design process. So using these 4 grids, a system can be digitized using the principles that were described earlier in terms of the spacing and the orientation of the grid. The second part of the tools is to create topologically sound networks, drainage networks in which flow is always towards the outlet, and all of the tile lines are connected together. Typically in on-screen digitization, it is possible to not have the lines connected. They might be small space that can only be seen on exploding the system. Also, one might digitize a line from upstream to downstream and another line from downstream to upstream. This tool, these tools, it reorients, it removes all of these discontinuities, the dangles or the overshoots, and it also reorients the numbering of the nodes to make sure everything is from upstream to downstream. But it generates new tile nodes, recreate and connect the tile network, and reorients the layout network to create a unidirectional flow system. Okay. And what the final task will be a network which is topologically sound, and then which can be passed to the third section for burying and sizing. The first tool takes the nodes and takes the layout and nodes which are close to each other within a certain distance of each other. It joins them together so that there are no overshoots and dangles and fractures in the network. Again, for this particular tool, the steps are outlaid. You select a new node layer, select the fields, and then the parts that are needed are specified in the input. So for example, it says you need to do the vertical part index, and then there's a field in the file that was created for the vertical part index, etc. And so it's easy to follow what the inputs are for each step. And finally, there is a routine for reorienting the network for the unidimensional flow system. The third part is to generate the network geometric attributes, such as the depth of the endpoints of each node, as well as the flow direction, and also to determine the flow order in which flow is done, and also in which the network is buried. So there are 5 tools to do this. The first one determines the network upstream flow areas, generate network flow orders, generate the geometric attributes, calculate cumulative flow lengths on the tile lines, and then generate elevation points and reference fields for burying the tile and also getting the flow. The first thing is to determine the net stream, the network upstream flow line. The input of this would be the output from the previous routine. Each of these follow on the other. Each one uses the output from the previous routine. And here one has to specify the field that the tile is coming from and the tile to field. And these names are the same names as that are in the required file. Eventually, all of these will be in one routine and they won't be exploded as they are here, but exploding it shows the various steps. And so doing that, then the output would be the flow layout file. Next thing from this, generate the flow order. One generates using the flow layout file, it determines the order in which each lateral or each line should be processed, so that an upstream line is always processed before a downstream, a line which is downstream of it, all the way back to the outlet of the system. Then there is the overlay of the DEM over the system to determine the endpoint elevations for each of the line. And then these endpoint elevations will be used for burying the network. Once the network is buried, the next thing to do is to determine the flow lengths for adjoining segment. To determine for any pipe, it determines the cumulative flow length upstream. And this is used for sizing the pipe. Then there's a tool for generating the elevation points and the reference fields. The reference fields are the one that are used to determine what the surface elevation, the depth of the upstream node and the depth of the downstream node, etc., and the slope of a pipe for each of these tile lines. Okay, so once all of that is determined, part 4 is the actual burying and sizing the network, where it calculates the optimal elevation depth for tile placement. It telescopes the pipe sizes across the field, it sizes the pipe from the upstream end to the downstream end, whereas the burial would be from the downstream end to the upstream end. And there's a cost analysis for all of the pipes in the drainage network. And then the outputs are exported to other formats which can be used by drain installation programs. The first step is to determine the buried depth at for each section of the pipe. And the inputs are specified, things like the order in which it should be buried, which was calculated in the previous section, the length, the elevation of the first and the last points, the 2 nodes for each tile, and then the other parameters like what depth should the tile be buried between. And what's usually specified is a required or preferred minimum depth and maximum depth. And there's also an absolute upper depth, and typically the upper depth is set so that the tile isn't shallow enough to affect tillage operation or to be affected by tillage operations. And then there's a maximum depth. The maximum depth is usually set by the equipment which is used for installation. Each tile machine has a maximum depth to which it can, an absolute maximum depth to which it can operate. And so these are used, not only the preferred depth, but the absolute minimum and maximum depth. The algorithms try as much as possible to keep the tile between the upper and the lower depth, the preferred, but there may be instances where it is outside of these depths, but it is never outside of the absolute upper and lower depth. After all of the tiles are sized and are buried and the slopes are determined, then using the upstream flow lengths and the spacing of the tile, it determines then what the flow should be, what the size of each pipe should be for the system. One thing about this thing is that it is possible to decouple the drainage intensity and the drainage coefficient. So there are 3 ways how the drainage, the drainage coefficient of each pipe can be determined. It can be set at the drainage intensity, and also it can be set at values greater than the drainage intensity. So typically for the laterals will be set at the drainage intensity, and the default for this program is to set the submains and the main at 25% bigger than the drainage intensity. However, it can be assigned the pipe material as well as the drainage coefficient can be assigned for each individual pipe in the system. After the pipe has been sized, the next thing to do is to determine, it determines a cost of the system based on a pipe size pricing table. The price size piping table will use NRCS average estimates, the NRCS cost share price for installation for tiles of various size, which might vary a lot from the actual price might vary a lot from one contractor to the other. And the general consensus from the contractors that have looked at the NRCS values is that the NRCS values are higher than the prices that they usually charge, mainly because of they have to work competitively. They have to, and so they can't afford to go to those prices. But that's the best estimate. We are working on so that the user can specify his own price table in order to do the pipe cost analysis. After that is done, then the design can be output to different in different formats. It can be output as a shapefile. It can be output as a CSV file. And we are talking to various design programs to find out the various formats that they would use in their installation. For example, we are going to add a DXF format for based on discussion with one commercial program for pipe installation. Okay, thank you very much. And that's just an introduction to the Illini drainage tool. And next we will go through an interactive example where we use the tools on a practice field. There is more details about the drainage tools can be obtained by scanning this QR code. Then it takes you to a manual for using the Illini drainage tool. Thank you very much.